Okay, can you see the projector screen okay? All right. So you want to go to here, piazza.com, and you'll find handouts there. Also, you'll see discussions. I mean, you can start a discussion if you want. If you have a question that pops up, and you can start a discussion, or you can answer the questions. Go ahead and answer those. It takes me some time to get to them. So go ahead and, you know the answer, or if you think you know the answer, or you can help out, just put it up there. And so when you go to piazza.com, I sent out an invitation for this. And so just bring up Piazza, just here. And then you'll have to set up an account. And so setting up an account is pretty easy. And let's go through it really quick here. I already have an account, obviously, but there are two ways you can start an account. You don't need an invitation for this, although I emailed invitations to you earlier this morning if you're on the official roster. If you're not on the official roster, you can it's easy to set up an account. You just go here, students get started, and then you look up the school, like for example, El Camino, and we'll just search here, Emmanuel. There it is, El Camino Community College District, and then the class would be Chem 4. And actually there's only, is that right? Chem 4, it's wrong. Fall 2018. I need to change the name, shoot. This is the wrong section number. So I'm going to edit that. Let me go ahead and actually I can't. I'm not signing in here. I'll sign in and fix it later. But go ahead and register for this by going to El Camino. I think I'm the only Chem class in here, so there's no other Chem classes. So just select this one. And the class access code. The class access code is just Chem 4, all lowercase like this, no spaces, just Chem 4. Class access code. And then we could join as a student here. Okay, there might be other classes there. This is free. We'll just join the class. Okay, then it asks you for email, username, this kind of stuff. So a few things you'll have to do. But I'm just going to log in here, and I'll just show you. What we have. That's been a while. I've got all my passwords. Once you're in, this is what you'll see here. And so I posted this today. And so we'll hit on this message. This is one of the handouts I was supposed to give today, except I don't know what happened to my handout there. I'll have it for sure. I should have it tomorrow, but I'll check on it. What happened this afternoon. I'll talk about the course tomorrow. Sorry. The only thing I wanted to talk about today is the required materials in case you're going to the bookstore to make any purchases. And so the textbook for the course is this Crocolici and Peters Introductory Chemistry, and it looks like this. So this is a custom published for El Camino. It's an expensive book, unfortunately. You only use it one semester. Okay, then we have this item number 2, which is the supplemented laboratory manual. It's loose leaf, it's plastic shrink wrap. You'll see it because they're going to be side by side. You'll look, Chem 4, Chabot, these are the required materials. You'll see on the bookstore shelf. There are a few other things that you'll need. You'll need a scientific calculator. If you're continuing on through Chem 1B, you want a scientific calculator that has the equation solver function built in. It's one of these, these programmable and graphing calculators aren't officially allowed in this course. So you might have a fancy, $100 calculator, but you're not supposed to use that here. And so you have to fall back on one of the SAT/GRE approved calculators. Now, a calculator like that would be something, I'll show you what calculator I use. I use the Casio FX115ES Plus.
It's an expensive calculator.
I'm sorry?
That's an expensive calculator.
Yeah, well, it depends on where you buy it. It's a 16. A lot of people recommend like the TI-30 or something. The TI-30 is like a $10 calculator, but I don't recommend that calculator at all. I'd rather spend an extra $7 or something, or double the price almost, and buy this because this is so much more powerful. This calculator has a solver function, so you can solve more complex, like the quadratic. Do you remember the quadratic formula? It's tedious. This one, all you do is you just plug in A, B, C, and it'll spit out X1, X2. It's much easier, and this is allowed on standardized tests, so it's not a problem. In Chem 1B, you have to solve the quadratic over and over again, and it just becomes too time-consuming. And so this one solves up to third-order equations, which is nice. Third order would be cubes, like ax cubed plus bx squared plus cx plus d. That one. And so it's a nice calculator, this one. But there are others, like Texas Instruments has one. It's like the next level, beyond the standard basic one, the one you want. And so I recommend this. You might as well just get used to it if you're continuing on in science. If you're continuing on in science, this is probably the most powerful non-programmable calculator you can get. And so it's worth it. And for a lot of classes, they don't allow programmable calculators. It's too much to track. And also this would serve as a good backup calculator in case something malfunctions with your programmable calculator. So look into this. All right. So that's item number 3 here, is the non-programmable scientific calculator. All right, item 4 here is the quad-ruled composition notebook with Chem binding. So it looks like this. This is what we're going to use as our laboratory notebook. Okay. Chem binding means that the pages are permanently bound here. They aren't meant to be ripped out. Okay, or we don't want the spiral bound or the other versions where you can tear out the sheets easily. So this is for our lab. Well, some people buy an extra one for their homework. It's nice to have your homework all in one notebook. And so a lot of people end up buying 2. They aren't that expensive. I bought this one at Staples. I think it was like $2 or $1 on sale. I bought it on sale, but I don't know what the current price is. Okay, the safety goggles. We only have one type of safety goggles in the bookstore. Those are called visor goggles. They have a green visor on them. And so if you don't have safety goggles, you have to use these. If you do have some safety goggles already, I have to take a look at them before I can approve them for laboratory use. So if you have some safety goggles, you can bring them in. I will take a look because there are different types of safety goggles out there. There are ones that are for splash and impact protection, and then there are ones that are just for impact protection. The ones that are just for impact protection, they usually have a lot of vent holes. Those vent holes can allow splashes or vapors to easily get in your eyes. And we want something for splashes. The most common splash that happens is things splash up. This, and so you need a good seal around the bottom. A lot of the impact ones will have holes on the bottom for ventilation, so they don't fog up. Visor goggles, these don't fog up easily, and these are the most, well, at least based on student surveys, these are the most comfortable for that. All right, I'll have some like Sharpie pens. Sharpie pens are good for writing on glass. So they're handy. You might want to get one for laboratory. You won't need it right away. But I'll have some for loan. Lab coat or apron. Lab coats and aprons, these are mandatory now at universities. Like UCLA, you're required to have a lab coat. Lab coats, the last lab coat I bought was on Amazon. It was $17. So it's worth it because normally at the end of the semester, all my clothes have holes in them from splashes and other things, stains, holes. You don't want to wear really nice clothes to lab. Also shoes as well. I had, when I was working at UCLA, I was working in a research lab at UCLA, and one of my lab mates spilled one drop of thiol. It's a class of compounds that skunks use for their odor. He spilled one drop on his brand new, very expensive sneakers. And he tried to bleach it out. He tried so many different things to kill the odor. Usually bleach works. I think he was pretty ginger with bleach, but he ended up throwing them away because they smelled too bad. So lab coat was good, and appropriate footwear. Of course, you'll need good footwear. Sandals aren't allowed in the lab. Open-toed shoes. And this is another thing that UCLA is requiring, nitrile gloves. You can buy nitrile gloves. I prefer nitrile gloves over latex gloves. Nitrile has a better resistance for most chemicals. After a while, these gloves are not supposed to be used forever because after a while, the gloves are like sponges and slowly certain chemicals soak in. And eventually, once they penetrate through, then it's free diffusion in. That is, they can easily get through the glove. And so there's a finite lifetime you can use the gloves depending on what type of chemicals you're using. Most of the chemicals we're going to be dealing with are what we call a water-based or aqueous, dissolved in water. That's what aqueous means. And so the gloves are pretty good for aqueous, called solutions or mixtures. And so nitrile are good. Nitrile also breathe a little bit better than latex, so you can wear nitrile gloves comfortably all day long. Once you get used to it, it takes time to get used to wearing gloves. When I first started wearing gloves, I didn't like it, because it was hard. But now I'm so used to it, it doesn't bother me at all. It's easy. I started off the nitrile a lot better. So these are things you'll think about. Probably bookstore is quite busy right now, but these are things to think about getting or should think about getting. All right, I'll talk more about the other material since we have time. Okay, also, this is the course information sheet. Also, here on Piazza, we have the syllabus here, 1174. I was thinking in an effort to save paper, I would just post these online, but I'm going to give you hard copies of this tomorrow. If I give you hard copies of this tomorrow, then we'll talk about it in depth tomorrow. But we're going to just jump into the material today, Chapter 1, Introduction to Chemistry. And we want to do Chapters 1 and 2. 1's pretty short, 2's a little longer, 3's a lot longer, so we'll probably start 3 this week. Then our lab days on Thursday. So our lecture days are going to be Monday, Tuesday, Wednesday, and this time, this always confuses me. It's 11 to 1:05, and then 11 to 12:50, and then 11 to 1:05. So I just wish it was just a consistent, regular end time. Just 15-minute difference here. Labs start earlier, 9:30, and a little earlier, 12:40. Lab days on Thursday. We're going to start lab on Thursday here, but this experiment is pretty simple. So you don't really, it's not that involved, so you don't really have to prepare much for this particular lab. Okay. Same thing with this second experiment. For the first experiment, we don't need safety goggles. Same thing with the second experiment. You don't need safety goggles, you don't need lab coat, you don't need protective shoes. You'll be all right. But by the time we get to experiment 8A, you're going to need that stuff. You know, the safety goggles for sure. If you want a lab coat, get it. But you'll definitely have to have proper footwear to participate in that lab. All right, so this is a basic schedule. The exams are going to be spread out. You know, they're going to be 4 exams spread out, except at the end. Since we only have 16 weeks. So the first exam is at the end of the 4th week. Second exam's at the end of the 8th week. Third exam's at the end of the 12th week. And fourth exam is at the end of the 15th week. So this is a little shorter. There'll be a little less material covered, but the exam will be worth the same number of points. Basically the same number of questions on it. And then you look here, from exam 4 to the final exam is only 1 week. And you know, at the university they have something called a dead week, in which there are no classes. You just study for finals, but unfortunately we don't have that here, or fortunately, it takes less time. And so, you know, we're actually going to be talking about new material here, chapter 19 stuff, and then take that on the final there. And so what it means is you'll want to keep up to date, you know, in all the material, because this is a comprehensive final exam, so from chapters 1 through 19. You don't want to forget the earlier stuff. You want to keep up to date there. You can do all right on the final. All right. Well, that's a brief breakdown. I'll talk more details tomorrow, and then you can see, you know, take a look at getting on Piazza, and you can take a look at the handouts. Well, I didn't start off as a chemistry major. I started off as a geology major. There are no geology majors. No. I started off in geology because I like outdoors, that kind of stuff. And so I stayed as a geology major until I hit this course called mineralogy. We were looking at minerals, their properties, etc., identifying minerals. And then when I got to mineralogy, you know, we had to identify these minerals. You know, what is this mineral based on the color, based on the shape of the crystals, based on, have you ever heard of a scratch test? A scratch test is you have a porcelain plate and you scratch the mineral on there and it leaves a fine dust. And that gives a more consistent color because it depends on how big the crystal is, you know, what color it looks like. For example, salt crystals. If you have table salt, what color is table salt? Is it white or is it colorless? What color are table salt? Well, when you look at table salt, it looks white, right? But if you look at an individual crystal of table salt, does it look white or does it look colorless? It's colorless, you know? And so the size of the crystal will definitely play a part in the color and how you perceive the color. And so geologists scratch it and see. As long as, as long as the porcelain plate's harder than the mineral itself, scratch test works. If the mineral's harder than the porcelain plate, then it just leaves scratches in the porcelain plate. You have porcelain plate dust. But there aren't that many because some of these porcelain plates are pretty tough. Some of them are made out of aluminum oxide, which has, have you ever heard of the Mohs hardness scale? Like diamond's a 10. You know, aluminum oxide's like a 9 on the hardness scale. So that's pretty hard stuff. But yeah, we use that kind of stuff, and I thought, wow, that. And I remember my professor. My professor was saying there are people who have 30 years of experience as mineralogists, and they still misidentify minerals. And I was thinking, misidentify minerals? How could they do that? In this day and age. And so then, at the same time, I was taking chemistry, and I thought, oh, chemists they wouldn't misidentify; they'd get it correct each time, right? But that was a little bit naive because chemists would use some kind of instrument to do that. Well, you can't take you can take some pretty sophisticated instruments out there, but they're expensive. But this is just what you can do with a very simple kit and with your eyes, to identify minerals. So chemistry had a bigger appeal to me at that time, and so I switched majors. But it turns out I didn't really have to switch majors because, they're geochemists and geologists do use a lot of the same instruments, the fancy instruments that chemists use. So I started off at Santa Barbara City College as a geology major, and then I transferred to UCLA as a chemistry major. And there I finished my bachelor's in chemistry. And then I went to UCSB and I got my PhD in inorganic analytical chemistry there. At UCSB I worked on with the materials research laboratory there. We're looking at different materials. And I'll talk more about it as we go along. But anyway, what got me interested in chemistry, or science in general, what got me interested in science? And that brings up the question, what do scientists do? What would you say scientists do? If you're thinking about, if somebody asks you, what do scientists do, what would you tell them? I'm sorry? Research, yeah, they do research. But sociologists do research as well, and I guess that's social science, but it seems like everybody will do some research on the internet. So maybe we can be a little bit more specific.
Scientists tend to explain the world around them through observation.
Okay, explain the world around them through observation. That sounds pretty good. Well, that's actually what got me interested in science and chemistry specifically, because I was interested in the world around us. I was interested in how things in the world around us work. Because I've always, let me tell you, it was like when I was a geology major, I was thinking, okay, maybe I'm going to major in auto mechanics or geology, because I like working on cars and mechanical stuff too, right? And so I was thinking, that's kind of fun. But I was interested in how cars work, how they operated. But then, chemistry is a lot similar to an auto mechanic, because auto mechanics are interested in how automobiles work. Chemists are interested in how the world around us works. How at least coming up with an understanding of the world around us. And when we come up with an understanding of the world around us, it's like, let's say you're interested in dogs, right? If you're interested in dogs, you want to understand, dogs. Well, how do you approach that? How would you just say, well, I want to understand dogs, then I just can Google it, or do you have an understanding of dogs? Or maybe you're not, or whatever else, whatever other field you're interested in. How would you approach that? Observation, right. You just kind of observe dogs, and you do some research, see what's been observed, and then you just accumulate that knowledge, right? Well, that's the same thing. Okay, we aren't studying dogs in this course, we're studying chemistry. Well, now, what do chemists study? Well, chemists study matter, and what is matter? Matter is what we say, the physical material of the universe. It's what the universe is made out of. It's what wood is made out of, plastic's made out of, metal's made out of, minerals are made out of, that stuff. And so chemists study that. And so it's like, you want to study dogs, you observe the dogs, you do some research on the dogs, you find out what's been written, you take your own personal observations. Well, as chemists, we do the same thing. We observe matter, we research matter, see what's been done, and then we study it in the same way. We don't just, there's been a push away from memorization. I guess not so much anymore, but for a while, a lot of people are saying, oh, you don't need to memorize anything. If you're going to be a dog expert, would you need to memorize anything? Well, would there be anything of value to memorize? Yeah, you'd probably have to memorize a lot of stuff. A 10-pound dog, what's the dosage of flea medicine or something like that, or this or that. There's so many things you'd probably have to memorize. Well, the same thing. Unfortunately, in chemistry, you're going to have to do some memorization. That memorization is going to take some time. But is it all memorization? When you study dogs, is it all memorization? You just get a book and memorize everything? No. There's a lot of observations. There's a lot of other stuff. Well, the same thing with chemistry. It's not all memorization, but we do need memorization to build some kind of fundamental, foundation to better understand things. And so I'll talk about that. And so let's take a look. I'm going to, also on Piazza, I'm going to post these, the PowerPoint. And there's some copyright stuff, so you're not supposed to share this or use this inappropriately. But I'll post this for you guys to, since you're taking the class, for you guys to download. Let's do that. And so you'll have access to these PowerPoints as well. And so let's go ahead with the slideshow.
When should we have the book by next class? Or?
The sooner the better. That way you could do the reading. But I'll have the PowerPoints as well.
Does the book come with the access code, or can we buy a used copy?
You can buy a used copy. You don't need an access code. The book does have online homework, but we're going to forego the online homework, which is OWL. And so you might need the access code for OWL. For the PowerPoints, I'll post those on Piazza, so you won't need to. The book's website is also a good source of teaching resources like sample quizzes and this type of stuff. So it's worth checking out. All right, so we'll just dive right into the material, and then these PowerPoints were made by the publisher, and so these pretty much follow along the book. But what I'm going to do is sometimes I don't follow along the book, but I left the PowerPoints as is, so you know how I deviate from the book. You can compare it with what the PowerPoints say versus what I say. And so even though you have the PowerPoints here, I recommend that you do take notes. You said, when do you need the book by? And I said the sooner the better, but in reality, what's most important is not the book. In reality, for exams, this type of stuff, the most important resource should be your notes, because this book is 738 pages, give or take. It's a lot of pages, and so there are some people. This is what happened to me as a student. I love books. And, I have a lot of very thick books, over 1,000-page books. But I ran into a problem. This hit me like my first or second quarter at UCLA. I took this class. I think it was engineering class. The book was 1,600 pages or so. 1,600 pages in 10 weeks. And then the way I used to study is I used to study from the book. I just read the book. I try to read the book like 3 times or something like that. Some professors at UCLA recommend reading the book 5 times. Can you read a 1,600-page book 5 times? No. I couldn't, because I'm a slow reader, especially in science. I timed myself once. I read 1 chapter, and at UCLA you could have like a over 1,000-page reading load in literature, because literature you could read pretty fast, right? And so I had literature classes. I'd read like 10 pages, see how long that took me, right? And then I read this engineering book. I'd read 10 pages, see how long it took me. Well, 10 pages took me 2 hours to read, compared to 10 pages in literature, which took me minutes. It's a huge difference. And so I ran into a big problem. I couldn't study the way I used to study, because the books were a lot less complex, a lot shorter, a lot less detailed. And so Then the notes, whatever is important, I put into my notes, and I had a good set of notes. So studying, 100 pages of notes versus 1,000 pages of text, 100 pages of notes is the way to study for the final. So for preparing for finals, it makes it a lot easier if you only have to review 100 or a couple of 100 pages of notes versus 1,000 pages of text. And so I didn't even highlight the book. Anything that was important in the book that I would highlight, I wrote into my notes as annotations in my notes. So I wouldn't have to ever open the book for studying for the final. And in fact, that's the way I kept it. Once I started doing that, I never opened the book for the final. I only opened my notes. My notes were accurate. My notes were accurate because I'd cross-check it with the book. And so I used the book to make sure that I wrote everything correctly, or that the instructor didn't make any, or whatever. And so, you could get by without the book for a little bit. I know the bookstore is going to be busy, so if you want to hold off on getting the book, it's not going to be a problem. But make sure you do take notes. Should be good. One thing that the book has is they have these like learning goals or learning outcomes. This is just the chapter outline: Introduction to Chemistry, Lavoisier and the beginning of experimental chemistry, Introduction to Chemistry, Science and the Scientific Method, Science of Chemistry Today, and Active Learning. So it's a pretty short chapter. Actually, this chapter doesn't have learning objectives. It just jumps into it. So we'll just jump into it as well. Is that okay if I turn off these lights here? Yes. All right, so chemistry. Chemistry they define as science that studies how molecules behave. I don't like that definition. I think that definition is way too narrow. Chemists don't just study molecules. You know what molecules are? Like H2O. You probably heard of H2O molecules. H2O molecules make up water. These are these tiny particles. I prefer the dictionary, and even the dictionary definition's off a little bit. But let's take a look, because I copied the dictionary definition into the course information sheet. This is from the American Heritage Dictionary. I like number 2, the definition. Number 2, the composition, structure, properties, and reactions of a substance. Substance is just material, matter. That's a substance. This is stuff that makes up the world around us. And so we study, what is it made out of? What is it made out of? How is it structured? How is it built? Kind of thing. Based on the composition and structure, then we can understand its properties. This definition, though, doesn't fit what we chemists do. This definition's off a little bit. And I'll explain why that is, because we often group reactions and properties. Reactions are just another property of the substance. So reactions are grouped with properties. And then we subdivide properties. So I'll talk about that when we get there. And so I like this definition a little bit better, but it's not perfect. So going back to this. Now this one, molecules, not everything forms molecules, and we'll talk about that later. So this is why I don't particularly like this, but it's okay. We'll just go with it because this is what the book is going with right now. What are molecules? Molecules are the smallest unit particle of pure substance that can exist independently and possess the identity of the substance. That's not entirely accurate. Chemists ponder on things that make up the universe. Well, the molecules, when we think about the universe, a lot of the universe consists of atoms. Atoms. You know what atom is very abundant in the universe? You know what atoms are? Atoms are different than molecules. Atoms are like these single particles, whereas molecules are, if you take these atoms, which are these balls, and then connect them, then we have molecules. And so this slide, there's some problems with this slide. So you just know, you don't have to know the specifics of it, but it's a little too narrow. Not only do comets ponder molecules, but they ponder other things as well in the universe. You know, the things that make up the universe. The things that make up the universe would be atoms and other things like called subatomic particles, energy, etc. But we'll see shortly that we get into a more modern way of thinking about this. Here's something about Lavoisier, the father of modern chemistry. He authored this. Somebody can pronounce that. Published that book, or the manuscript was published in 1789. Marks the beginning. Prior to this, you know, chemistry had its origins in alchemy. You know, one of the big goals of alchemists was to convert lead into gold. Have you ever heard that? Wanted to convert lead into gold, transmutate elements, you know, that was one of the big goals. But here, he's really credited with starting this. And what do scientists do? Scientists, in order to understand how things work, you know, in the world around us, we have to observe things, you know. And scientists, what they do is they observe nature. And so scientists observe nature. So you know, how do we observe nature? We want to do this, you know, as quantitative, like as detailed as possible. You know, there's quantitative versus qualitative. You know, quantitative is taking precise measurements, precise and accurate measurements. Qualitative are just like less precise. You know, the degrees to which that deviates can deviate quite significantly. Some qualitative is just a gut feel, but scientists tend to be much more quantitative than qualitative. But anyway, the conductive experiments. The experiments are, you know, taking detailed observations of things, the phenomena, or whatever else, when we do the experiments. You don't have to know the names, but we'll just see some of his experiments. Okay, based on observations, you know, we could, for example, debunk a theory, this phlogiston theory or phlogiston theory. You know, this all matter has the ability to burn contains phlogiston. In the process of burning wood, phlogiston is lost and ash remains. You know, and so there's some mysterious matter or whatever consisting of this. However, based on observations, you know, Lavoisier took some phosphorus, mercury, did some burning experiments. And his observations contradicted this theory. And so if there's some kind of contradiction to the theory, then the theory no longer really works at supporting it. And so this resulted in a new hypothesis when a substance combines with oxygen and air. And where did that come from? You don't have to know this. So this is just Lavoisier. And I'm not going to test you on any of this here. I'm just kind of giving you some background. And so these are the observations. So this is what scientists do. We predict observations. Not predict, we take observations. If you take observations, you aren't making any predictions, right? You know, could you predict what's going to happen? This is burning phosphorus. You know, could you predict what's going to happen? Could you predict how much the balloon shrinks? Can you predict, et cetera, et cetera? No, this is kind of hard. What scientists do is they'll just observe. After they take observations, and they do this a lot, so you take another sample of phosphorus, then you can predict. You know, we can predict because we see a pattern. You know, and some people will do this. Some people will do this with like dog behavior. You know, certain breeds of dog might behave this way, and so you make a prediction. Well, that dog's this breed. Maybe that dog will behave this way. Maybe, and then you see. Right? Well, for something like this, you know, we burn the phosphorus. Maybe the next time we burn the phosphorus, we can predict. Phosphorus is a lot less complex than a dog, that's for sure. But so it'd probably be easier to predict. But anyway, it turns out that there's less air in the jar for burning. And so this is where it came out. This is a mercury burning experiment, and the same type of thing happened here. Less air in there. And so we have these. And so Lavoisier is credited with this, which is what we call the scientific method. Scientists, what they do is they take observations, they observe nature. And from this, I'm going to change this a little bit here. Let's talk about modern scientific method. This I will test you on, the scientific method. These are the general steps of the scientific method, you know, and not everything has to fit these steps. It's not like 1, 2, 3, 4. You know, some things just happen serendipitously, and other things evolve in different ways. But this is what scientists do. This is what I did when I was working in a research lab. This is what I did every day. You know, I take observations, do experiments, and that kind of stuff. And so, what scientists do is they take observations, and then you just don't take observations. So, for example, we could take observations. Let's take an observation. We have these raw observations. Let me just show you. If I have that. Here, I think the desktop has been. So we might get some observations, like something like this, and write them down. These are some observations, scientific observations here. You know, got a bunch of observations, numbers here, so quantitative. You know, got more numbers. You can measure these things. You got a bunch of observations like this, you know, individual observations. Now what? Well, it's easy. Like, for example, burning phosphorus. You observe burning phosphorus, the air kind of collapses. Interestingly enough, the total weight doesn't change. The total weight stays the same. Well, you got observations like this, and sometimes it's even more. So, you know, sometimes you take thousands of observations, right? Then what do? You got all those observations. What's that?
Propose an explanation.
Okay, go ahead. Propose an explanation. You know, I got some numbers there. It goes from big to small, actually negative to positive. I got these numbers. Although, you know, this is not really fair, you know, because there's more to this chart than what we see. But, you know, eventually, how are you going to propose an explanation, or how are you going to propose anything? What we do when we're looking at, let's say we're looking at different breeds of dog, and you're looking at Doberman Pinschers. You want to just observe one Doberman Pinscher and say all Doberman Pinschers are the same kind of thing? Would you do that? No, you'd probably want to take lots of observations, right? You take lots of observations, and then what you're going to notice are what? You're going to notice maybe every one of them are totally different. If every one of them are totally different, then you have a condition where you have to memorize everything, because if every one of them behaves totally different than the others, then there's nothing common except maybe the way they look, right? And so that means, well, if you want to understand a dog, you're just going to have to memorize, right? But do you think every one of them are they going to share any common traits or common features? Would you think so? Yeah, I mean, yeah, they should. I mean, they're going to grow big or whatever. And so what we do in science is the same kind of thing. We look for patterns. You know, because you look at all this looks like crazy. You know, this is so much random stuff. Or is it random stuff? You know, if this is totally random stuff, then you got to memorize it line by line. But fortunately, it is not totally random stuff. There are certain patterns that exist there. And so that means that saves us quite a lot because that saves us from having to memorize everything. But does that completely free us from memorizing things? No, we still have to memorize a lot of things, just not as much. And so we look for patterns or trends. In science, when we look for patterns and trends, oftentimes we'll make graphs, because sometimes when you graph things out, you can better see a pattern in the numbers or whatever else. So we look for patterns and trends like this. So, let me give you some classic. Do you know Isaac Newton? Have you heard of Isaac Newton? Who's Isaac Newton? Inventor of calculus. Also, have you ever heard of Newton's laws in physics? Yeah, Newton's laws. Well, I remember Isaac Newton because I remember watching cartoons when I was young, and then there was an apple in a tree. Apple fell in the tree, fell onto his head. Right, that was the observation. Did you see that? Yeah, and so Newton. Okay, something falls. An object falls. Right. Is there any pattern to that, or is it different each time? If it's different each time, then you got to memorize, everything. Oh, the drop A, or is there something consistent about this? Is there something? Okay, then what we see is, okay, there's something consistent. There is a pattern there, and that pattern is a consistent pattern. Now, when you come up and you look for these patterns, you know what the most concise way of defining a pattern is? The most concise way of defining a pattern, ooh, that dropped fast. Is that a very concise way of defining a pattern like that? It's pretty fast. Maybe if I drop it, for higher distance, it'll take a little longer. But still fast, right? No, that's not the most concise, because scientists, they want to be quantitative. Quantitative meaning they want to nail it down. So you want to time it. So how long did it take, right? And then time it, and then drop it from higher, and then how long did it take, right? And so you take a whole bunch of observations, the stopwatch or whatever else. I remember doing this in physics, taking the stopwatch, measuring. There's got to be some coordination there. Well, they're going to be scattered because sometimes you don't hit it just right. It's better if you have a beam, that triggers. It's more consistent than pushing the button. But you see a pattern, and this pattern, turns out that the most concise way of defining the pattern is mathematically. If you can write some kind of mathematical equation for this pattern, then that's the most concise, most compact way of defining the pattern. And so, from the observation, Newton, apple falling from the tree, he's noticed some patterns and trends, right? And from these patterns and trends, he figured out there's a mathematical relationship. Those mathematical relationships we call laws. And these would be the laws of physics. And the laws of physics you can do. And so from the Newton's laws of motion, we can make a prediction. How long will it take to fall from 15 feet? And then we can predict that using math, right, based on what we saw as a pattern. And so these laws are very useful, because these laws we can do to predict. At least make some predictions. And that means the amount of memorization we do is a lot less. Because if somebody asks you, okay, I'm going to take it from 20 feet, tell me how long it's going to take. Well, then you might say, if you're the memorization type, you might say, okay, drop one from 20 feet, let me time it, and then I'll tell you how long it's going to take, because I'm going to memorize how long it takes to drop from 20 feet, right? But is that the way you want to approach everything? No. We got to do that, because initially we got to take the observations, get those, down, and then figure out this mathematical pattern. But ideally, we'd like a law. The law, these are typically empirical mathematical equations. I'm just going to call them empirical equations. Newton had to devise some calculus to to come up with some of these patterns. This is why calculus was, I think, developed, because of the patterns. The patterns couldn't be described by the current mathematics. But not just Newton. One other mathematician is credited with discovering calculus. You call his name? Newton and Leibniz?
Leibniz.
Okay. Yeah, I just remember Newton, there's two people credited. They come out. I think they came up with it independently. But anyway, these are typical empirical. Now, what do I mean by empirical? If you can't read my writing, let me just tell me. I'll rewrite it. Empirical. Have you ever heard the word empirical? Empirical equation. Empirical equations, empirical means they come from observation, from measurement. And so these are equations that are based on observation. So how did Newton come up with his laws of motion? Well, how Newton came up with his laws of motion, we're just observing these and looking for some kind of pattern. Well, what do we do in science? Well, that's all we do. We just observe things and look for patterns, these patterns. But these, based on observation, these laws, these are laws of nature. Laws of nature are different than, let's say, like administration of justice laws. Laws of nature are, we have something called rules versus law. In this class, we're going to learn rules as well as laws. So what is the difference between a rule and a law? Does anybody have any guesses or ideas? What do you think?
Rules can be broken.
Yeah.
Whereas laws define things so that it's not alternative.
Right. Laws, as our book is going to say, laws shouldn't have exceptions. There are going to be some exceptions once in a while, but laws typically, if there are a lot of exceptions to law, then we're no longer going to call it a law. We're going to call it a rule, and there are going to be lots of exceptions to the rule. Rule of thumb, rule of whatever. The law shouldn't have that. And so these laws of nature are not violated. So if they are violated, then that's really not a valid pattern. It's not a good valid law. So this. So we take our observation, and then let's just go down this way. Skepticism, predicting, testing, revising. Well, that's kind of like this pattern. So here's where I'm deviating from the book a bit. We got these patterns and trends. And then we come up with laws. And these laws are good, but what do you think? Do you think the pen would drop in the same amount of time on the moon? Why not? Okay, but that's it. In the law, does this law, for example, talk about gravity? Where does gravity come into this law? This law is based on empirical observations. You're right. You're absolutely right. The gravity on Earth is different than the gravity on the moon, and so it shouldn't, right? But where did the gravity come in? Did Newton first think of gravity? Is this the way it works? Did Newton first think of gravity and come up with a hypothesis? The pen's going to drop this fast because of gravity. Did gravity come first and then the law? Or did the law come first and then gravity? Well, get to this. Actually, we're going to take a break. We'll take a break like We'll take a break now for, let's take a break for, let's say, a little over 10 minutes. We'll start again at 12:20. Is that good? Let's take a break.
We'll leave our things in.
You could leave your things